Okay, we have some more things to talk about with rational functions. But so far we know, we've talked about what a rational function is. We discussed what vertical asymptotes were. We saw something called a whole or a removable discontinuity and the difference between those and vertical asymptotes and when they happen. And we're going to go back to our old example. This was the rational function that we've been talking about for a little while. Maybe Yoda's here. And this is the function f of x equals x squared minus 2x minus 3 over 2x squared minus x minus 10. And the big question I want to answer right now is, what do things look like? Well, first of all, remember that we saw these awesome vertical asymptotes and discussed how we found those. Those happened because these were points where the denominator was equal to 0, and so they were problem spots that the function avoids. But as you look at this function, do you see any other sort of places that the function seems to avoid, or values that the function seems to approach? Maybe is a better way of thinking about it. And this time, instead of thinking horizontally, instead of thinking vertically, think horizontally. And you can see there seems to be this horizontal line that the function approaches. As x goes to positive infinity, we get closer and closer to this line. And also as x goes to negative infinity, we get closer and closer to this line. So the next big question that we want to answer is, what do things look like at positive and negative infinity for a rational function? And how can we determine that just from knowing the function, knowing the algebraic function? Okay, this is called, well, as x gets bigger and bigger, as x does go off to positive infinity, say, think about what these numbers would do. Say that x was 1,000,000. 1,000,000 squared is a really large number. And negative 2 times 1,000,000, that's minus 2,000,000. It's not that big compared to 1,000,000 squared. 1,000,000 squared is really big. If you took 1,000,000,000 squared, that would be way huge. And these other terms become less and less of a factor. Same story on the bottom. This leading term sort of starts dominating. So as x approaches plus and minus infinity, the two leading terms dominate for sure. And what do I mean by leading terms? It's the term on the top with the highest degree on a variable, or the highest power on a variable, and the term on the bottom with the highest power on a variable. Those are the two leading terms. They dominate the function. And so as x gets bigger and bigger, either positive or negative, we really only need to look at y equals this part of the rational function. So y equals x squared over 2x squared, which is, these cancel, a 1 gets left behind, or y equals 1/2. This isn't the function, but this is the clue as to what how the function is behaving as x goes to positive and negative infinity. And this is definitely this green line. This is a horizontal asymptote, and this is 1, 2, 3, 4, 5. So this is y equals 1/2. The leading terms tell us where this is called a horizontal asymptote. And the formal definition of a horizontal asymptote is f of x will have a horizontal asymptote at y equals a. Here it was y equals 1/2. If as x goes to plus or minus infinity, the function itself, the y values, go to a. And that's happening. As x goes to positive infinity, the y values of the function are approaching y equals 1/2 from either direction. So this is our horizontal asymptote. And in this particular case, here's our horizontal asymptote. Okay, this is the strategy. To find a horizontal asymptote, you look at, for a rational function, you look at the two leading terms. And how that ratio behaves is how the function will behave as it goes out to positive and negative infinity. So this is, we'll call it our finding horizontal asymptotes strategy. And we had sort of a strategy to find vertical asymptotes, and now we have a strategy for finding horizontal asymptotes. So we'll want to remember this. We just look at the two leading terms. They tell us the whole story as x goes to positive and negative infinity. Okay, some of you may have noticed something that vertical asymptotes are not allowed to do that horizontal asymptotes are allowed to do. They are allowed to have the function actually cross them. See right here, the function crosses this horizontal asymptote. That was absolutely forbidden with the vertical asymptote. But horizontal asymptotes are a little different. They really are only telling us end behavior. They're only telling us what's happening out at infinity or what it's approaching at infinity. So horizontal asymptotes get away with a little bit more than we let vertical asymptotes do. So unlike vertical asymptotes, the graph can cross. The graph of our rational function can cross a horizontal asymptote. Because horizontal asymptotes just describe end behavior of the function. And so what's going on in the middle is not really pertinent to the horizontal asymptote. Okay, so we're going to look at two other examples now. For our second example, we're going to look at a rational function that's really similar to example one. The only thing I changed was I made this, the power on this leading term in the denominator, cubed instead of squared. So our job here is to find the horizontal asymptote, and we remember that our strategy for finding horizontal asymptotes is to look at the two leading terms, the leading term in the numerator and the leading term in the denominator, and we'll examine those. So if we're looking at something with just those two leading terms, what would that look like? We have x squared here, x cubed here. We can cancel two of the x's on the top and the bottom. A 1 gets left behind here. And we have 2 over x. Remember that we're interested in finding out what's happening as x goes to positive and negative infinity. As x gets really large, anytime you have a really large denominator, then the whole fraction will go to 0. If this is fixed here, and the denominator is getting larger and larger and humongous, then the whole thing is going to go to 0. So this will go to 0 as x goes to plus or minus infinity. And so we expect a horizontal asymptote at y equals 0. Because that's what the leading terms are behaving like. So a picture of this function, it's right here. This is this rational function, the graph of this function. And so we look at how it's behaving. Well, as x gets larger and larger, as x does go to positive infinity, it looks like the function is approaching y equals 0, this horizontal axis. And as x goes to negative infinity, it looks like the function is approaching from below, but still approaching y equals 0. So what we expected turned out to be totally true. The horizontal asymptote is at y equals 0. Okay, let's look at a third example. This will be the last example on horizontal asymptotes. And this time, our function is going to be f of x equals x to the fifth minus 2x minus 3 over 2x cubed minus x minus 10. I'm not changing much. I'm just changing so the leading term has a higher power than the denominator leading term. So our strategy to finding horizontal asymptotes is to look at these leading terms and find out what they're doing as x goes to infinity. Those two leading terms put together would look like x to the fifth over 2x cubed. This simplifies. There's 5 of them up here, 3 of them down here, so 2 of them get to stay. These 3 get canceled out, and we have x squared over 2. This is basically like 1/2 times x squared. What does this go to as x goes to positive or negative infinity? So this number is getting really big in the numerator this time. So really large numerators, this is fixed. As it gets bigger and bigger and bigger, as it goes off to infinity, this as well goes to infinity. So y approaches infinity. That's the end behavior. What that means is there is no horizontal asymptote this time. And so sometimes that happens. In a picture of this function, the graph of this function, as x goes to negative infinity, it shoots up to positive infinity. It's coming down here, and there is some sort of vertical asymptote right here. We weren't asked to find it, so we're not going to spend time looking for it right now. But the function does have a break right there with the vertical asymptote, and then it comes back up, and then as x goes to positive infinity, it's going to shoot off to positive infinity. There is no horizontal asymptote here. So, in general, say that we had a function that was a rational function, and it starts out with some number times x to some power over bx to some power. With rational functions, we have these 3 cases for horizontal asymptotes. Oops. If m equals n, if these powers are equal, this is what we saw in example 1, then the horizontal asymptote There will be one at y equals a over b. In example 1, we saw this at y equals 1/2. Whatever the ratio of the coefficients of your leading terms are, if these powers are equal, m and n, this is kind of the critical thing to examine, these powers here. If those are equal, then you will have a horizontal asymptote at the ratio of your two coefficients. That's the first case. If m is less than n, we saw this in example 2, you'll have a horizontal asymptote every time at y equals 0. It's because this power becomes so large. If this is a larger number, then it dominates, and this becomes really big down here. This can't quite keep up, and these whole leading terms go to 0. The third case is if the power on top of your leading term is larger than the power on top of the leading term there, then there is no horizontal asymptote. Now we'll talk about example 4. Which is really just our old example 1. It's this function. We've seen this picture before. But this time we want to talk about something we haven't talked about yet, x and y intercepts. And this is a concept that you've seen before. You've seen it with linear functions and other polynomial functions. And so our big question here is, when does the function cross the x and y axis? If it does at all. That's a question in a lot of applications. It's an important question to ask because it often is dealing with quantities at the beginning of your experiment or at the beginning of your observation, or when does a quantity equal 0? Those are important questions to ask in a lot of settings. Okay, to find x-intercepts, we set y equal to 0. This is something you've probably seen before. So there's no y here, but f of x, the name of the function, is acting like the y value. So we set that equal to 0, and we're going to solve this equation. Now a function is 0 if the numerator equals 0 and the denominator is not 0. So not a function, a fraction is 0 if the numerator equals 0 and the denominator is not 0. That has to be true at the same time. So if we want to solve this equation, we really only have to figure out, well, when is the numerator equal to 0? When is x squared minus 2x minus 3 equal to 0? And we can solve this different ways. We can factor it and then solve it. You could also graph this expression and see where the y value is 0. We're going to do the algebraic way. So we'll factor this. X, let's see, multiply to -3. and add up to -2. That should do it. And so x minus 3 equals 0, which means x equals 3, or x plus 1 equals 0, which means x equals -1. These are the two places that the function will equal 0. So these are the two places the function equals 0. If you plug 3 in for x, you'll get a 0 for an output. If you plug -1 in for x, you'll get that y equals 0, or the output is 0. So these are our x-intercepts. X-intercepts always mean where the y value equals 0. Okay, next we have to find the y-intercepts. This is slightly easier. To find y-intercepts, we just set x equal to 0. So to find the y-intercepts, we just plug 0 in for x. 0 squared minus 2 times 0 minus 3 all over 2 times 0 squared minus 0 minus 10. That'll equal, those go away, that goes away, -3, goes away, -10 equals 3/10. So y equals 3/10. When x is 0, y equals 3/10. This is our y-intercept. So 3, 0, -1, 0. For this rational function, these are our x-intercepts, sometimes called horizontal intercepts. And the graph shows that that looks pretty reasonable. At 3, 0 and at -1, 0, the graph is hitting the x-axis. So this is an x-intercept. And then we know that 0, 3/10 is our one y-intercept, or sometimes called vertical intercepts. And looking at the graph, that looks right. If this is 2, 1 is right here, this looks like about 3/10. Okay, so we know a lot of things about rational functions. We know what a rational function is. We know that to find a vertical asymptote, or possibly a hole, we see where the denominator of our rational function equals 0. That was the strategy. We had a strategy for finding horizontal asymptotes. You look at the leading terms, and find out what they're doing at positive and negative infinity. And x and y-intercepts, to find x-intercept, you set y equal to 0. To find y-intercept, you set x equal to 0. So we've learned a lot of things about rational functions. The next video we'll look at some specific examples that will be similar to what your homework questions are like.